Okay, so now we're gotten to the chapter on rational functions and equations, and everybody loves these because this is algebraic expressions in fraction form. And so two of the things that everyone loves most are fractions and algebraic expressions, and of course rational functions and equations. Put them together. So let's see what we've got in this chapter. We're going to graph rational functions. We're going to talk about vertical asymptotes, horizontal asymptotes, slant asymptotes, all of these things. So we're going to solve rational equations algebraically and graphically. Don't forget that you can do that. And we're going to solve some inverse variation problems. So remember, a rational function is a function in which we have basically two polynomials with a quotient. And of course, the bottom can't equal to 0 because then we have asymptotes, right? Or sometimes we just have little holes. We don't always have asymptotes, and we'll talk about that in just a second. What the difference is, why sometimes we just have a little hole in the function and sometimes we get an asymptote. So let's talk about vertical asymptotes. Vertical asymptotes is kind of an imaginary vertical line on a graph of some rational functions, not all, that the graph nears y the graph nears the asymptote as y goes toward infinity or negative infinity, but it never really touches the vertical asymptote. So these are found by setting the denominator equal to 0, but they are places in which the denominator is not 0, because if the numerator is 0, there's some canceling that can be done because of the fundamental theorem of algebra. So let's talk about this rational function. And let's find the vertical asymptote, and then we can just sketch the graph real quick. So what do we see for a vertical asymptote on this? So remember, we set the denominator equal to 0. So x minus 1 equals 0, so x equals 1, right? So we have a vertical asymptote at x equals 1. Well, let's look at this. I'm going to change colors too, so you can see where I'm at. Okay, so we have a vertical asymptote at x equals 1. So that means right here we have a vertical asymptote, which we usually denote by a dotted line. So now let's think about some numbers that we put in here. What if I put 0 into this equation? So let's set some x's and some y's up. If I put 0 in for x, I'm going to have 0 plus 1 over 0 minus 1. That's going to be negative 1. So when x is 0, y is negative 1. Looks like that's going to be right here. Okay, what happens when x is, let's say 2. I can't do 1, so let's say 2. That's going to be 2 plus 1 over 2 minus 1. 3 over 1, or 3. So let's do that one. 1, 2, 1, 2, 3. That's here. So I still aren't really seeing what's going on here. So let's put in a couple more. Let's put in negative 1. What will happen if I do negative 1? That's going to be negative 1 plus 1 over negative 1 minus 1, which is 0 over negative 2, which is 0. So at x equals negative 1, I have 0. And what about negative 2? What would happen at negative 2? Negative 2 plus 1 is negative 1 over negative 2. That'd be 1/2. So that's here. What about negative 3? I'm starting to get an idea what this looks like. So negative 3 plus 1 is negative 2. Negative 3 minus 1 is negative 4. Did I get that right? Wait a minute. Make sure this one's right. Negative 2 plus 1 is negative 1. Oh, this should have been 3. Negative 2 minus 1 is negative 3. It should be negative 1/3. That's okay. That's about where it is anyway. And that's 1/2. So it's a little higher. So I'm starting to get an idea what this looks like. And this looks like that. Now if that looks like that, this probably kind of does the same thing. So this was 1/3, this was 1/2. So what is 3 going to do for me? Let's see, 3 plus 1 is 4. 3 minus 1 is 2. So that's going to be 2. So looks like we almost do the same kind of thing. And that's kind of what we look like. So let's check that with Desmos. And we have x plus 1 divided by, and I put this in parentheses, x minus 1. Oops. I think I used the wrong slash. There we go. Whoops. Let me get rid of this. Okay. And that's kind of what it looks like. So we see this imaginary line right here that it never touches. We kind of see one going this way also, don't we? So that would be a horizontal asymptote. Interesting. We'll talk about those in just a second. Okay. A horizontal asymptote. So if y approaches a number, just some number, as x approaches infinity, or as x approaches negative infinity, and all this means is gets really big. I say approaches infinity, gets really big. Or x approaches negative infinity, gets really big in the negative direction. Okay, either way, the graph of y equals f of x has a horizontal asymptote at y equals a. Let's go back up to this and let's look at this for a second. What seems to be happening in this problem? Looks like there might be a horizontal asymptote right here. And that looks like it's happening at y equals 1. And let's think about why that would be. What if, and the way you can find these, you can put really big numbers. So what if x was a really big number, like 10,000? What would happen if x was 10,000? We'd have y equals 10,000 plus 1 over 10,000 minus 1. So that would be 10,001 over 9,999. Well, what is that? Oops. Pretty close to 1. That looks really darn close to 1. So you can see what's happening. As x gets really, really big, we get really close to 1. What happens when x gets really, really negative? What would happen? So if I was at negative 10,000 plus 1 over negative 10,000 minus 1, what would happen? Just the opposite of what just happened, right? This is going to be negative 9999 divided by negative 10,001. And that's pretty darn close to 1 also. So you can see what's sort of happening as we get really big numbers for x. This is going to get closer and closer to 1 because these two things aren't really going to matter much anymore. Then you're just looking at x over x at this point. So all you're looking at is what we call the dominating terms. And the dominating terms are the x's. If I make x go really, really big, 1 and negative 1 become like Nothing. If I'm at 10 trillion, what's 1? Nothing. Very little, right? What's adding 1 and subtracting 1 means nothing. So this gives me a way to determine horizontal asymptotes of a rational function. So let's say I have my two polynomials up here. So this situation we just looked at is where n was equal to m. So the degree of the numerator degree equals to the denominator degree. So once again, we look at our dominating coefficients. So we're going to look at the dominating terms. Actually, I want to say the coefficients of the dominating terms. And the dominating terms are one that creates the degree of the polynomial. So if the numerator and the denominator, their degree is the same, that means you have a situation like x over x, 1x over 1, and assuming that x isn't 0, because as x gets really, really big or really, really small, it's not 0 anymore. This just becomes 1. Or it just becomes a ratio of the coefficients of the dominating terms. So then if we look at if n is less than m, so this is a situation where we have something like x squared plus 1 over x cubed plus 5, for example. In this situation, if you got really, really big numbers, if you put millions and millions in for x, would 1 and 5 stand a chance? Not at all. So then you would just be looking at x squared and x cubed. Well, again, assuming these aren't 0 because they're very, very large on one way or the other, because we're talking about n behavior here. So what happens when x gets really, really big? Well, if we had x squared over x cubed, we would say that's 1 over x. And when x gets really, really big, what does 1 over x do? Gets really, really small, right? 1 over 10 million is almost 0. So this gets closer and closer to 0. This becomes closer to the ratio of the coefficient of the dominating terms. So what happens when this is the opposite way around? What happens when I have something like x squared minus 2 over x plus 1? Well, again, when x gets really, really big or really, really small, what happens? These don't matter anymore. It's like big deal. 10 trillion squared and then minus 2. Who cares if I minus 2? It doesn't make much difference. So x squared over x, that would just go kind of like x, which x is getting bigger and bigger. So what's y getting? Bigger and bigger, right? So that means we have no horizontal asymptote. This just heads off toward infinity. Or negative infinity, I should say. So that just heads off toward the stratosphere, just like x is doing. So as x gets bigger, y just keeps getting bigger and bigger also, which means we don't have a point that we get closer and closer to without touching, like we do on these two. Okay. So, and remember, these are the degrees. So these are the degree of the top is more than the degree of the bottom. This is degrees are equal. And this is the degree of the top is less than the degree of the bottom. Okay, let's do some examples. Oh, I didn't do any. I think I'm supposed to make up my own here. Okay. So let's say f of x equals 3x squared plus 2x minus 1 over 2x squared plus 3. Okay. What is the horizontal asymptote of this equation? So let's look at the dominating terms. Let's just look at the squares. Once these do 10 million squared, even 10 million isn't going to even make any difference anymore. 10 million squared is going to. So we're going to look at the dominating terms. These x squareds, once x gets big, these two are going to dominate everything. So crossing off the x squareds, what am I left with? 3 halves. So this is going to get closer and closer to 3 halves. Now let's look at this one. Say g of x is 3x minus 1 over 5x squared plus 2x plus 2. Okay, let's look at the dominating terms. The dominating term on the top is x. The dominating term on the bottom is x squared. Now what's going to happen? Doesn't matter that that's 3 and 5. What really matters is this x is not going to stand a chance against the x squared. So this is going to get smaller and smaller. So you're going to end up with 3x or 3 over 5x. That's still going to go to 0, right? Just going to keep getting tinier and tinier. So this one is 0. What if I have 6x cubed minus 2x plus 1 over 3x squared plus 5x plus 3. What's the horizontal asymptote to this thing? Again, what dominates everything? These two. These two will dominate everything once x gets really big. And once x gets really big, this is just going to go toward, well, the 2x. So as x gets bigger and bigger, y is just going to get closer and closer to 2x, which is just going to get bigger and bigger. So we don't have a horizontal asymptote. Y just goes out to infinity or negative infinity. Okay. So let's talk a little bit about slant asymptotes and missing points. Now, if the degree of the numerator of a rational function is 1 more, just 1. Okay, so like we have x squared plus 3x plus 6 over x minus 1. This is 1 more degree than this. Its graph approaches what we call a slant asymptote. We can find by using this method. Divide the numerator by the denominator. Okay, so I want you to think about this. So like we did in the last section, we could do this division problem, right? We can actually use even synthetic division. 1, 3, 6, 1, 1. It's 1. 4 times 1 is 4. We end up with 10. So we rewrite this. It actually looks like this. X plus 4 plus 10 over x minus 1. So I want you to think about what's going to happen and what this thing is going to look like when this gets really big. So if x got really, really big, what would happen to this piece over here? Oops, go away. What would happen to this piece? I want you to think about it. If x is huge, this would go to 0. So what would this function go to? This line. So we get a linear function plus this rational expression for the remainder. Well, this linear function is our slant asymptote, because this is going to go off to 0. It's going to get closer and closer to 0. So this is going to tell us what happens. So in this case, our graph, let's see, we have a vertical asymptote at 1. Change colors here. We have a vertical asymptote at x equals 1. So we have this. And we have a slant asymptote at x plus 4. It's 1, 2, 3, 4, and up 1 over 1. So we have a slant asymptote going like this. So that's what that looks like. And all I need to do now to even know what this even looks like is I can put in, let's put in 0. If I put in 0, I would get 6 over negative 1 or negative 6. So I have 0, x equals 0 is y is negative 6. So it looks like it goes like this. And then it goes off that way. And then it's going to go off in the other direction. So these are my two asymptotes. And now I'm going to go, I know it goes off in the other direction, and it's going to go opposite that side. So it kind of goes like this when it does it. So we can get an idea exactly what that looks like. I graphed one thing. All I did was find the asymptotes, and that was easy. So we can get an idea of what something like that looks like. Okay. So let's do another example of a slant asymptote. So we need to find the equations of the vertical, horizontal, and slant asymptotes, if any, for the graph of this function. So let's look at this. X squared plus 2x plus 7 over x minus 3. So what is a vertical asymptote? We set x minus 3 equal to 0, so x equals 3. So let's check to see if it's a vertical asymptote. 9 plus 6 plus 7 is not equal to 0, so the numerator is not 0, so therefore this is a vertical asymptote. Horizontal asymptote, do we have one? No, because this is larger than this. This degree is going to overtake this x. So we have no horizontal asymptote. But since it's one larger, we do have a slant asymptote. So 1, 2, 7. 1, 2, 7. We divide by the 3. Bring down the 1. 1 times 3 is 3. That is 5. 5 times 3 is 15. Plus 7 is 22, so we have x plus 5, and then 22 over x minus 3, which again, that's going to go off to 0 as x gets large. So our slant asymptote of this function is going to be x plus 5. So we can get an idea of what this looks like if, so let's draw our asymptotes. Let's put our asymptotes in red. It looks like we have an asymptote at x equals 3. So let's see, 1, 2, 3. So there's our vertical asymptote. We have a slant asymptote with the equation x plus 5. So let's see, 1, 2, 3, 4, 5. And we go up 1 over 1. So it looks like we go like this. Oop. So I always like to check at what happens in 0, just so I know where to put it. So let's see, at 0 I have 7 and negative 3. So that's like negative 2 1/3 or so. So at 0, at x equals 0, I'm at y equals negative 2 1/3. 1, 2 1/3. So I know I'm in here somewhere. So I know that I'm in this part. So I know that goes that way, and I know this goes this way. So then I have up in this area up here. So let's see what this looks like. This is one a little hard to see. So let's see what happens up here. There we go. Well, this is stretched out a little, so you can see this is up to 25 and negative 20 and negative 22, it looks like, into 22. So when we stretch it out a little bit, we can actually see what's going on. And you can see that just about what I drew is just about right. And so we can see that it has this asymptote right here, the 3. And here's the asymptote, our slant asymptote that has the equation x plus 5. See, it crosses the y-axis at 5, and then it goes up 1 over 1 from there. So, there we have that one. So, let's take a look at missing points. So, let's look at this, x squared plus 2x minus 15 over x minus 3. So let's look at that on Desmos and see what it looks like. So let's go to Desmos, and I've already got it graphed, and you're thinking to yourself, wait, that's a rational function. Why does it just look like a line? And the answer to that question is because, and why don't we have an asymptote at x equals 3? So there should be an asymptote. Let's see, this is right here. Why is there not some kind of asymptote right there? Because x can't equal 3 in that particular graph. So let's take a look at something. Let's go back to what is this? So the thing is, remember when I said the vertical asymptote happens where the denominator is 0, but the numerator isn't? Well, I would have said a possible vertical asymptote at x equals 3. But look what happens when I put 3 in the top. 3 squared plus 2 times 3 minus 15. I get 9 plus 6 minus 15. Oops, that's 0. That's the issue. Because of the fundamental theorem of algebra, that tells me that x minus 3 must be a factor of what's in the top. So what I want to do is I want to redo this function at the top so that it has x minus 3 and something else. Well, what would that be? X plus 5, right? So what we really have here is this is equivalent, but if I cross these off, that's fine, except x cannot be 3, or I'm crossing off 0 over 0, which is completely an indeterminate form of anything. Okay, and if you want to get the idea of why 0 over 0 is so bad, I want you to think about what 0 over 0 should be. 0 over 0 should be 3 things. Well, first of all, a over a, any number divided by itself, is usually 1, as long as a is not 0, right? So it should be 1, but 0 divided by any number would be 0, as long as that bottom isn't 0, right? And then a divided by any number is not possible because that tends off, if you take that, if you make this number smaller and smaller, that goes off toward infinity. So truthfully, we're looking at something that should be 1, 0, and not possible, or tend toward infinity, all at the exact same time. So that's why 0 over 0 is actually worse than just regular dividing by 0, because it's just indeterminate. We don't even know what to do with it. It doesn't go off to infinity, it doesn't go to 0, it doesn't go to 1, or does it go to all 3 at the same time? Boom, we don't know. So